a great talk, Sustainable Building Practices and Beyond with Carl Seville and Rob Howard. I'm going to let them introduce themselves because they're that way and they have such great words for themselves. So I'm going to throw it over to Carl.
Thanks, Will. Okay. Carl Seville, my company's SK Collaborative. I was a contractor for about 25 years. I owned a company called Sawhorse, which some of you may know if you've been in Atlanta for a while. And luckily got out of that before the recession. And now I do rebuilding consulting. And if you look over there, that's an affordable multi-family project that I did the Earthcraft certification on. So we basically inspect and help people build better buildings. I got a very condensed session on sustainable building. Applies to tiny houses as well as any building that's out there. Tiny house goals, just house goals. Efficient, healthy, comfortable, and durable. We do this by applying building science, also known as BS, to those of you. So I'm going to give you a little tiny bit of BS here. Building science is the interactions between heat, air, and moisture. It's basically all it is. Think about heat. Always moves from hot to cold. There are three ways it moves. It goes through conduction, which is through a solid, convection, which is through air movement, and radiation, which is from surface to surface. And those diagrams below, does anybody know how we control? They're controlled differently. How do we control conduction? What materials and products do we use to control heat through a solid? Insulation. Okay. How do we control convection? That's heat moving through air. How do we control it? Pardon? No, if you want to control it, you want to stop it. Air sealing. It's closing up the gap. We don't want it to move unintentionally. And then radiation. How do we, from surface to surface, how do we stop heat from moving from surface to surface? Pardon? Well, yeah, shading does a really good job. There are things called radiant barriers in attics, window glazing, things like that. So those are the three ways we basically stop heat. Then air movement. Air movement always moves from high to low pressure. It only moves through holes. If your house has no holes, the air will not move. So our houses should be very tight. Everybody house should breathe. Everybody thinks your house should breathe. Never. A house should be as leaky as a submarine. And then you intentionally ventilate. A house should not leak anything. When you shut the door in a house, your ear should pop. It should be that tight. And I live in a house like that.
Did you slam your doors when it's all?
No, but if you slam it, right now, the house I just built, if you shut the door downstairs, all the doors rattle in their frames upstairs because it's so tight. It moves through holes, and it needs a driving force. If you have holes and there's no driving force, then it doesn't move either. The driving force is wind, generally, and ducts. If you have ducts in a house that flow air around, they will tend to change the pressure. There's some other stuff, but it's too involved for this conversation. Heat moves through air. This little diagram on the right, this thing, to me, explains everything about building science in our humid climate. We're going to start with the heat moving through air. Movement is either heat gain or loss. When it's hot outside, it's going to gain heat on the inside. When it's cold outside, it's going to pull heat out from inside the house. Less air movement means much better temperature control and improved comfort. Who here, when it suddenly gets cold outside, their house gets really cold pretty quickly? Okay, if you have a tight house, it can hold its temperature for 3 or 4 days. It can drop 30, 40 degrees outside, and your house will stay comfortable for days without the heat going on. Same thing with the air conditioning, except for the heat. So, an airtight house that is also well insulated. It's basically like a cooler. It holds its temperature. So the second half of this is vapor moves through air. In our climate, vapor movement is really important. If you look at that diagram, that's a sheet of plywood. If a sheet of drywall. If a sheet of drywall has no holes in it, it will diffuse 1/3 of a quart of water through that sheet of drywall over a season, over a heating air cooling season. If you cut a 1-inch square hole in that, 30 quarts of water will go through that. So what this really happens is, what this means is, let's say when you're air conditioning your house in the summertime, a lot of what we do is take humidity out of the air. So if your house is very leaky in the summertime, and you put the air conditioning down, the air conditioning takes the humidity out of the air, and the air is dry inside and wet outside. Moisture always moves from wet to dry. So you basically have all this moisture outside your house, and it goes, I'm going in. And it leaks in through all the holes, and your air conditioning works harder and harder. When you seal up the house, it basically doesn't require that much heating and air conditioning. The opposite happens in the wintertime. Who has a house that gets dry in the wintertime? Like, you're gonna get sinuses, but somebody's gonna have sinuses. Okay. People think that's because the heat from your furnace is low. It is not. It's the exact opposite in the summertime. In the wintertime, it tends to be dry outside. The humidity is fairly low. Inside, we tend to use, we bathe, we breathe, we cook. It creates moisture in the house. So in the wintertime, all that moisture in the house goes, it's dry outside. I'm going to go outside. That's why your house is dry. So when you have a very tightly sealed house, it does not get dry in the wintertime, or as dry. So that's really the essence of why we air seal. And I always tell people, if I had to choose, I would choose air sealing over insulation up front. Because I would not want to choose, but if I had to, I would. And a little bonus, when you do air seal a house very well, it stays clean. Dust, pollen, things don't go inside. I've been in houses, built houses, they're very tightly air sealed, and they just don't get dirty. Okay, moisture movement. Moisture always moves from wet to dry. Three key things, two things. Liquid, moisture is rain, and then vapor, which you basically just talked about how to do. So rain gets in your house from gravity. You have holes in the roof, gets in. It moves from capillary action. If you don't fill the house right, you have like nails going through it. It can leak through those little holes. Those big to small holes get sucked in your house. And momentum. If you get a driving rain, your house is not really well sealed for moisture, water will get in. Okay, that's the end of my BS. Now we're going to get some specifics of it. So controlling heat movement, we use insulation. And insulation has to be combined with an air barrier. They have to work together. If you have an insulation that is not an air barrier or does not have an air barrier, it basically doesn't work. So fiberglass insulation by itself, if it isn't combined with an air barrier, essentially doesn't work. It does not serve its purpose, does not give you the insulation. The air barrier has to be complete, continuous, and in contact with the insulation. I'll get some diagrams in a minute to show you that. The air barrier can be on the inside, it can be on the outside, or it can be both. Insulation, basically two kinds of insulation. What we call air permeable, fiberglass, cellulose, mineral wool, and denim, like that blue jean insulation. Those need an air barrier that's a separate product. Whereas air impermeable, which is foam insulation, spray foam, and then rigid foam boards. They are the insulation and the air seal together. So if you use those, they basically seal your house up if you do it all right. Whether it's combined or separate, insulation has to have an air barrier to work. So controlling air movement is, when I say it's just geometry, it's planes, lines, and points. So the planes are the bottoms, the sides, the top of the house, which is essentially the floor, the walls, and the roof, and the ceiling. The lines are the seams, which is the bottom plate to the floor, the top plate to the ceiling of the roof, it's where the seams join, and then the windows and the walls. Doors to the walls, actually pipes and kind of connection. And then holes, pipes, wires, ducts, anything that goes through the edges. So we have to seal those things, and they're fairly simple ways to seal it. The walls, the floors, and the ceilings can be sealed with OSB or plywood, cheap material. They can be sealed with foam, and they could be sealed with drywall. I don't think too many mobile tiny houses have drywall, but drywall is basically a pretty good air seal. The seams sealed with caulk, foam, or tape, and the holes are also sealed with caulk, foam, or tape. That's basically what it is. So you have to look for every gap between in the planes, the gaps in the seams, where they turn corners, and holes in it. They all have to be sealed. You have to control moisture movement, and it's flashing your windows and doors properly is really important, and most contractors don't do it correctly. Flashing the pipes and the wires that come through the walls. One thing that contractors do all the time is they frame the house, and they slap the siding on right away. And then the insulation, then the HVAC guy comes through and drills a hole for the duct. Then the electrician goes through and drills a hole for a wire. And then the plumber goes through and drills a hole for a pipe. Every one of those is an air leak and a water leak, which will cause your house to be inefficient and wrong. So what you have to do is you have to build a house, make sure you have every single mechanical penetration through the house, tape, sealed, foam, whatever, to make sure it's watertight and airtight, and then put the sign on the house. If you're ever having a house built or renovated, make sure that happens. Controlling moisture movement, house wraps work well. It's like a Tyvek type product. Foam board that's taped, and zip sheathing. There's one of these houses out here that has the green board on it, zip sheathing, which is these are all, if they're installed properly, they're very good products. They cover air and cover moisture, and in some cases can cover air. The foam and the zip sheathing will also be an air barrier. The house wrap, paper house wrap, tends not to be a very good air barrier to seal the sheathing behind. So where are we? Your tiny house is now insulated, it's air sealed. You've managed the moisture. So what we have left are mechanical systems, which are heating and cooling. And I walked through these houses last night, and I had to think about mini splits like Rob's going to talk about. And I realized some of them have little wood stoves in them. So you could get a foot square. I was kind of pleased. So I didn't talk about wood stoves, but and then other stuff is water heating, lights, appliances, and any other equipment you have in the house. So HVAC, mini split heat pumps, they're energy efficient, they're quiet, they're slightly higher cost than some other options. They also work at great outside temperatures. I have a 2,600 square foot house, and I use 3 of these mini splits to heat and cool, no doubts. And I actually get away with 2 of them for one thing. And the great thing is they also work down at very low temperatures, very efficient. A simpler, less expensive solution that is louder and less efficient is a package terminal heat pump, or basically an air conditioner with a heating cycle. They generally tend to be, you've probably seen them in hotels or even in the window if there's a window in your house. They're single speed, generally, they're less efficient than noisy, but they're an inexpensive solution. Ventilation, when you have a house, when your little house is closed up, it's important to have it ventilated. You want to ventilate out any cooking odors. Especially if you have more than one person in a tiny house, just breathing is going to increase the carbon dioxide in the building. You want to get rid of some of that. When you shower, a lot of moisture is polluted. Using cleaning products, unless you're really careful what you use, cleaning products are going to stink up your house. And furnishings. So one of the challenges is when any new house, you can build a new house as pristinely as possible. It's hard to get furniture, this new furniture that does not have a lot of nasty stuff in it. Fire retardants, other chemicals, VOCs. Be careful what you bring in the house. So these are all pollutants, and we want to be able to ventilate them in the house. You first want to eliminate them by avoid bringing them in. And second, you want to ventilate them to dilute the air and get that. So it's spot exhaust that we put in kitchens and baths. You don't see too many of them in these houses because they're just too small. But if you think about a general house, baths have to have exhaust fans. Kitchens should have exhaust fans. You don't always do that, but you want to just have something that draws the sticky stuff out of the house. And then having some kind of whole house ventilation is useful. It can be exhaust ventilation, just use your bath fan to ventilate your house. Or you could use this great little product called energy recovery ventilator. It's a sort of magic box that brings in outside air, filters it, transfers some of the heat or the cooling to the inside air. And so, it's a very efficient way to keep the house healthier and more comfortable in the climate parts of the year when you're not opening and closing windows and doors. Water heating, interesting challenge. Fuel for water heating, you can use propane, you can use electric, use natural gas. If you're going to build, a house on a foundation as opposed to a house on wheels, it's the interesting challenge is using natural gas these days. And I found this out when I did my own house recently. Unless you're using your gas for heating, it becomes an incredibly expensive proposition. Because if you just say you're just water heating your house, or maybe just water cooking, you're spending about $1 a month for gas. You're paying the gas company $30 a month for the privilege of purchasing gas. So what you want to do is probably look at making the house all electric. If you're not using electric. Using electric for heat, you're generally in good shape, although you'll get a little more of the and the good thing is if you do all electric, you can use solar and basically get to net zero through it. In terms of water heating, you use a tank heater. If you have a small house, you have enough room to put a small tank heater. So you fit a 5 or 10 gallon heater. Tankless, if you have propane or natural gas, tankless is a very good option. Electric tankless takes enormous amounts of power to run. So I would recommend avoiding electric tankless heaters. They can be really challenging. They probably take more power than anything else you put in your house. Appliances and equipment, lighting. At this point, I still show CFLs on here. I wouldn't even look at them. LEDs, the quality is good, the cost is down. There's no reason to put anything but an LED light in your house. The color temperature is good, they last forever. Cooking, propane or electric. I use an induction cooktop in my house. I noticed one of these tiny houses has an induction cooktop. It's a great way to go. It's energy efficient, has perfect temperature control. If you're going to have a cooktop. Some of them don't even have kitchens in the building. The other thing I want to think about is equipment. There are things like phantom loads, computers, just doing cable TV boxes, TVs. A lot of those things have phantom loads. When you have a small, efficient house, sometimes those phantom loads can be extremely high, maybe a third to a half of your electric use in the house. So look at what kind of equipment you're buying and make sure that when it's in the sleep mode, it's really in the sleep mode. If not, unplug it or put a switch on it so it turns off when you're not using it.
So what's a phantom load?
Phantom mode is it's when a piece of equipment is turned off, but it's still on. The new TVs tend to be very low energy, like the old tube TVs. They would draw as much energy when they were off as when they were on, just so you could use your remote control. Cable boxes and DVRs are incredible energy hogs because they're always on and always running. The game systems, you just want to look at any piece of equipment that's got a remote control so it's on all the time. You want to check and see how much energy it's using. They're getting better in terms of dropping down to minimal load when they're off. Anything with a remote control has some energy use when it's off all the time. And that starts to add up. A computer, or a printer, TV, DVR, that can be half the electrical in your house. Let's see. Okay, so recap. We talked about insulation, we talked about air sealing, we talked about moisture management, mechanical systems. You end up with an efficient, comfortable, durable, and healthy house. So, actually, that little house on the top is the house I used to live in. It was 800 square feet. I lived in that for about 12 years. So I built a new house in front, which is even more efficient than this new one.
Are we giving tours after this?
My house, it's only a couple of blocks. That's my contact info, and I write a blog occasionally. It's called greencurmudgeon.com, so feel free to look at it and make comments. Okay, you're up, Rob.
Apparently we're going to do questions at the end. Hold that thought. Okay. Wow. So the title of my portion of the presentation is Design, Build, Perform, HVAC Systems for High-Performance Tiny Houses. That's an older picture of me when I had darker hair. I'm the Performance Construction Manager for Mitsubishi Electric Cooling and Heating for our Southeast Business Unit, which runs from Florida to Maryland. So this is about as close to home as I've been in a while. I actually live in Western North Carolina. Formerly was Director of Construction for my local Habitat for Humanity affiliate for 10 years. Was also a Sustainable Building Specialist with Habitat International for 5 years, so I've spent quite a bit of time in the Atlanta metro. And just by way of training, my background is a general contractor and a perforator. Who knows what a perforator is, by the way? Well, this is going to be fun. That's what one looks like right there. So this is the audience participation portion of the presentation. So it's time for you guys to talk. What is a high-performance home? What does that mean to you? What do you think of when you think of a high-performance home? Energy efficient, absolutely.
Low maintenance.
Low maintenance, I like it. Sure, yep. Maybe even off grid, yep. I heard somebody say tight. Something else? Low potable water use. So water efficient in addition to energy efficient. Yeah, I like it. Anything else?
Utilizing all the space.
Say again?
Utilizing all the space.
Utilizing space, yeah, absolutely. Space efficient as well. Longevity, so durable, right? How long should a house last? Forever. Wow, you have lofty goals. 50 years, I heard. Do I hear 100?
Yeah.
I actually, the first house I lived in is over 100 years old, so it's possible, right? If you go over to Europe, they get even older than that. We just happen to be such a new country, we don't really have that old of houses. Closer? Is this better? Yes. Oh, that I can hear myself. I don't like that. All right, I'll try. So, some high-performance home characteristics. Let's see if there's anything we didn't name already. So, up here I've got tightly constructed in terms of the fit and finish of the home. We said that. Tighter or limited ductwork. So, we're going to talk about whether or not ductwork is even necessary. But if we're gonna have ductwork for HVAC systems, then certainly that should be really airtight. I like to still ask people, how tight do you like your plumbing? We expect that to be pretty tight, right? So if you're gonna have ductwork, we should have the same kind of expectations. So a high-performance home should hopefully retain heat really well, at least if we're trying to heat the home in the wintertime. It should also be able to keep heat out in the summertime. But that high-performance home may also retain more moisture. So we're going to talk about the latent side of this as well as the sensible side when we're heating and cooling a home. And then as Carl mentioned, we're at the point now where homes, they're built tight enough that they really require mechanical ventilation. So not just the spot ventilation that we talked about out of kitchens and bathrooms, which pretty much everybody's accustomed to, but actual whole house mechanical ventilation so that we get good air changing, good mixing of air throughout the home. So we're also talking about efficient design, and Carl's already covered a lot of this, so I'm not going to dwell on it, but all of these elements go into making a more efficient, high-performance home. So we talked about insulation, air and moisture barriers, the thermal envelope, if you combine those, is often what we refer to, or the building envelope. You'll hear that term used a lot. Carl talked about lighting and appliances and just plug loads. And then, of course, I'm going to talk more about the HVAC systems. So when you think about building a high-performance home, who should be a part of the team that puts that home together? So, these are some of the suggestions. Builder or general contractor is obviously going to be a part of the team. The architect or the residential designer. Sometimes we now just have design-build firms where that's all sort of done in-house. Sometimes on large enough projects you may have a mechanical engineer involved, but oftentimes it's just somebody who offers load calculations or an HVAC designer. Do you guys do loads? There's a lot of companies around the Atlanta metro who offer that service, and we're finding more and more of those around the country now. Mentioned this person called a HERS rater. We're going to talk more about the HERS rating in a second, but basically think of it as somebody who's a verifier or a consultant, an energy consultant on the project. And then certainly I would suggest that your HVAC contractor should be a part of that team. Who else can you think of that might be a part of this performance construction team? Anybody else who needs to be the owner? That's a novel thought. So yeah, probably the owner should probably be at the table since they're paying for this thing. Anybody else? Plumber, electrician, other skilled trades, absolutely. Let's make sure they all get along. That's a good idea. Yeah, how about the insulation contractor? Not often considered one of your skilled trades, but I think we would agree they're really important on these jobs. So oftentimes the insulation contractor is now responsible for the air sealing details as well. So if we're going for a high performance home, then absolutely we need to make sure that we're on the same page with whoever's providing that insulation and air sealing service. Anybody else? That's a pretty good list. So what might be some performance construction goals? Are you guys familiar with any certification programs? Carl mentioned Earthcraft, which is actually started here in Atlanta by the Home Builders Association, right? And then run by Southface Energy Institute. Any other certification programs you're familiar with? Most of you have probably heard of Energy Star. You may be familiar with it through appliances, or you've seen the Energy Star logo on computers or any sorts of consumer electronics. But did you know that you can also have a home certified as Energy Star? And the person who does that third-party certification is called a HERS rater. Often, that's an acronym, by the way, so you'll often hear them referred to as Home Energy Rater or just Rater. EPA, who created the Energy Star program, later added another label on top of that called Indoor Air Plus. So now we're looking, as opposed to specifically at energy efficiency, making sure this is a healthy home with healthy air for people to breathe. The Department of Energy has now built on those two programs and created what's called the Zero Energy Ready Home. So now we're starting to move down that scale toward a zero energy home. Anybody familiar with Passive House? This is that super insulated, super tight structure, which Carl used a lot of those passive house techniques when he built his house. We're talking about, you know, those houses as he described that, you know, when you slam the doors, the toilet flushes, it's really tight. So, but also has very low heating and cooling loads, or the need for additional heating and cooling. Just your body heat can almost be enough to heat these, so they're incredibly efficient. And then again, when you get to the, you know, the end of that spectrum, we're now talking about net zero energy homes, by which we mean a home that can produce as much energy as it consumes over the course of a year. And then, you know, mention this idea of a HERS score. A group called ResNet is who created this index, and it looks, you know, sort of like a thermometer. So the idea is that the lower the better. It's kind of like a golf score in that way, not that I would know. But it does require an independent third-party inspector to verify a couple of things about the house, and that person is called a HERS rater. So it also provides a standard by which to compare one home to another. Think of it sort of like a miles per gallon rating for a house. So now we've got the ability, if you're looking at two houses side by side, how do you compare them in terms of their energy efficiency? You can try to get a hold of some past energy bills, you know, compare it that way, but a HERS score would be another way to do that. And as I said, the lower the score, the more energy efficient the home. So as we talk about these performance building programs, you can start to put these on the HERS scale and see how they compare one to another. So a typical existing home might be 130 on this scale. A new construction home would be somewhere between 70 and 100. I think 100 was the 2006 International Energy Conservation Code. So as the code continues to evolve, these houses improve and start going down on this scale. Energy Star homes, probably somewhere in the 60 to 70 range. And then we talked about the passive house. Now we're starting to get down into the 30s and 40s on this scale. And then again, if you have a net zero energy home, we're going to get all the way to zero. And actually, if you produce more energy than the house consumes, it would be considered a net positive home and could actually have a negative HERS score. So quickly, just want to run you through this concept of load calculations, because again, I'm coming at it from the heat and air side, and this is what we expect the heat and air contractor to know in order to properly size the heating and cooling equipment for your home. So how do they do that? So basically, a load calculation is a heat loss calculation. We're trying to determine what exactly do we need to heat and cool this home. How many BTUs per hour do we need to provide in order to provide heating or cooling? So, you know, we're going to talk about the summertime usage. We're also going to look at the wintertime usage. So you'll have both a heating and a cooling load. What are some of the factors that have to be considered? Well, we're going to look at basically everything in regard to the building envelope of the house. We're going to look at the roof, the ceiling, the walls, the windows, doors, lighting, appliances, and also just the orientation, the geographic location of the home. How does the sun affect that building as it tracks across it during the day? So yeah, I said that, orientation to the sun. And then, oh yeah, let's consider the people that we're actually building this house for, right? The owners, as you described them. So yeah, absolutely. If we know how many people are going to live in this home, then we can better adjust the size of the system to meet their needs. So there's basically two types of load calculations. A lot of contractors perform the one on the left, which is called a block load. So they're basically just pretending like the house is one big room, just like this, with no interior walls, no partitions. So how much heat loss or heat gain does that entire structure have? But if we really want to start dialing down or zeroing in on the individual loads throughout the home, we need what's called a room-by-room load calculation. We want to know what the heat loss and heat gain is in each of those spaces. So obviously the ones around the rooms around the perimeter that have more exposure to the elements, more windows, more glazing as it's called, would have higher loads than interior spaces. So some of the benefits of doing a load calculation, we want to properly size the equipment. We call it right-sized equipment in terms of the number of BTUs per hour that we need to provide. We want to be able to reduce duct loss, as we said earlier. If we're going to have a forced air HVAC system, then we want to minimize or eliminate duct loss. So one way to do that would be if you're gonna have ductwork, as opposed to running it through a hot attic, otherwise I like to call it the oven, why don't we bring that indoors so that that ductwork has a much better chance of providing the temperature air that you expect when it gets into the room. We need for the equipment to perform to meet the thermal needs of the home. So properly cycling air through the house to keep the temperatures consistent. And then we want to try to obviously eliminate any hot or cold spots in the home. It doesn't do you much good to have a room in your home that's always hot in the summer, always cold in the winter, so you can't really use it. Does anybody have a room like that in their home? Where might that be? Your room? That's nice. So, I mean, what would you attribute that to? Why is your room the one that's not comfortable? Yep, maybe it's an airflow issue. You know, it's a long duct run far from the unit. Maybe it's a leaky duct run. Maybe it's running through an attic or a basement, you know, or a crawl space. So, yeah, hard to say. Yours? Most of the apartment. Wow. You just need to move. So usually I hear bonus rooms, or some people refer to it as a frog, finished room over garage. I love that. So those are often uncomfortable spaces. So, you know, it's got all kinds of challenges with a garage below it, a roof above, and then those knee wall areas on the sides. So it can be really challenging to heat and cool. And a lot of times, you know, as a former builder, I can say this, we try to cheap out. Wow. We got really loud there. We try to use the same system that's heating and cooling the rest of the house to heat and cool that bonus room with a long duct run that it just never works well. So we see a lot of ductless heat pumps, or mini splits as we call them, used for those kind of remote room situations. So what does all this mean for tiny homes? So we're talking about small houses, right? In terms of the overall heated square footage, these are much smaller than typical homes. So they naturally have tiny loads as well. So while an average, I don't know what you consider to be an average size home, but an average size, let's say 2,000 square feet, might have a heating and cooling load of 2 tons, 24,000 BTUs. Well, how about a 400 square foot house or a 150 square foot house? We're talking about micro loads. So suddenly it becomes a real challenge to pick HVAC equipment that can go that low, because the smallest conventional heat pump is 18,000 BTUs. It's called a ton and a half. So 12,000 BTUs is a ton of heating or air conditioning. So if the smallest conventional system is 18,000 BTUs, is that going to be oversized for a tiny house? Grossly oversized. So what's the big deal? Why is it a problem? Isn't it better to have, too much is always better than not enough, right? Not in this case. Why not? Okay. See, you should be teaching this class. That's exactly right. Oh, see, now you tell me. I'm glad you waited until this point in the presentation to tell me. We got a mechanical engineer on the front row. So yeah, exactly. If you oversize the system, it's what we call it's short cycles. It actually cools the space too quickly. So believe it or not, air conditioning was not created to lower the temperature in your house. It was actually created to remove the moisture from your house. But how do we do that? How do we take the moisture out of the air? You can't answer this. We have to run air across a cold coil. So when that happens, that air reaches dew point, condensation occurs, and that's why we have a drain to the outside from air conditioning. So we literally wring the moisture out of that air by running air across a cold coil. Well, we have to do that over a certain period of time before we begin to remove any moisture. And if you cool that space too quickly, you don't get enough run time to do that. So we see this a lot in small homes, in high performance homes, and we're certainly seeing it in tiny houses. Yeah, certainly. The smaller it is, and if you go out here and spray foam one of these little houses, that's a tight that's a tight envelope, right? So as we generate moisture within that home, it's almost impossible to get it out if you don't have significant runtime on your heating and cooling system. So I would say the answer to this challenge is we need tiny HVAC systems. I don't know if anybody was here for the VIP event last night, but our Senior Vice President, Mark Kuntz, was one of the opening speakers, and he talked about the fact that Mitsubishi makes tiny air conditioners for tiny homes. So we make the smallest unit in the industry. We have a 6,000 BTU unit, so half a ton, which is, has anybody been through the tiny office out here today? If you haven't had a chance to do that, it's got one of the shorter lines, so I would encourage you to check it out. But we donated the equipment for that house, and it is our 6,000 BTU unit. And again, most manufacturers of this type of equipment start at 9,000 BTUs, or 3/4 of a ton. We have one that is 6,000 BTUs, half a ton. So just to orient you to the components of these systems, this is often referred to as VRF. You can't answer this either. Anybody know what VRF stands for? Somebody said it. Variable refrigerant flow. Yeah, exactly. So our commercial guys don't like it when I use this term because I'm a residential guy, but technically we do vary refrigerant flow in our system, so I still say we're VRF. But we're VRF heat pumps, I suppose might be the correct way to describe it. So there's two types. I'm generalizing here, but this is a single zone. You have one outdoor unit, one indoor unit, connected by a line set, and then of course you have some kind of controller. For most of our ductless heat pumps, it comes with a handheld remote control, and you may have seen some of those in the houses today. Over here on the right is what we call a multi-zone system. So it has a little larger outdoor unit we call it a condenser. And then it has multiple line sets that feed multiple air handlers inside the home. And there are a lot of different configurations. Most people are familiar with the wall hung, the high walls as we call them. But we also make a low wall or a floor mount. These are what's called ceiling cassettes. They're 2x2, so they're normally I look up and point at the grid, but there is none. So, but you've seen a grid ceiling in a commercial building or in a basement in a residential structure. So it's meant to go in those 2x2 ceiling grids. And then we also make ducted equipment. So if you have a house that's more compartmentalized, and you don't want to try to put a ductless air handler in every room, then we have, these are called horizontal ducted air handlers, if I can get that to work. That would serve multiple bedrooms, for example. And then we can actually connect up to 8 indoor units to one outdoor condenser by doing what we call a branch box. So this is sort of like a manifold in plumbing. So at that point we would run refrigerant from the outdoor unit to the branch box, and then it controls how much refrigerant goes to each indoor unit. So again, one outdoor unit and up to 8 indoor air handlers. So just to give you an idea of what some of these look like installed, this is kind of a tricky picture because you can't see anything but the register on the wall. This is meant to be a horizontal ducted unit. A ceiling recessed, again, these fit perfectly into a 2x2 ceiling grid, but they can also be installed in part ceilings. The only catch is you would have to have access to the top side for service. Floor-mounted units, which technically don't really sit on the floor. Typically, we mount these just above the baseboard, which keeps you from banging into it quite so much and keeps it a little cleaner. And then what we're really known for, which is our wall-mounted high walls, ductless units. You're not going to believe this, but some people do not like the look of our air handlers. I'm sure nobody in this room feels that way, but there are people out there who do. So we've come up with some creative solutions for people like them who don't like the look of these to make them blend in or disappear in the decor inside their homes. So if you happen to live in a log home, we can paint the unit to look like a log. It's not a problem. We can also get creative with built-ins and try to conceal the units. Can you see it? I can't see it, I don't know. You got like x-ray vision or something? It's behind this little grid, right? So I'm not going to vouch for the performance of this system because I don't know that they actually calculated the net free area on those louvers. They probably did not. So, and I hope they hinged it so that we can get in there for maintenance as necessary, but maybe it's just removable. Just like you can wrap a van or a car, you can also wrap a ductless heat pump. So this is pretty clever. They wrapped it to look like books on a bookshelf, and I'd say they did a pretty good job there. I don't know that I would have put the actual books quite so close to the sides of the unit there, but hopefully those aren't first editions. And then just the ability to integrate these into some kind of architectural feature within the home. So to me, this is a little more practical, as long as you allow for proper airflow around the unit. So these blow air out the bottom and they return air in the top. I would probably have given it a little more clearance than that, but that looks pretty clean. So just some of the capabilities of these systems, clearly high efficiency. Anybody know what the minimum SEER rating is for heat pumps now? 14 SEER, I think, right? 14 is now the code minimum. So like the FH06 that's in the tiny office out here is a 33 SEER system. So more than twice the required SEER rating. Variable speed operation, and that's a variable speed fan on the indoor air handler, as well as we said a second ago, variable refrigerant flow from the outdoor unit to the indoor. The ability to have individual room control, we'll talk more about that in just a second. Oh, sorry, getting ahead of myself. Quiet operation. Has anybody paid attention to that as you were walking through these houses today? You can barely hear these things run. You really almost can't tell that they're on. So they're incredibly quiet. And that goes for both the indoor and the outdoor. If you haven't done this, walk around the side of one of these houses and see if you can tell if the outdoor unit is running. Usually you have to put your hand in front of it and feel the air coming off of it to know it's running. They're incredibly quiet. And then we mentioned cold climate capability. We have a technology we call hyperheat. So if you're going to put one of these in a colder, up in the mountains or somewhere north of here, then we would certainly recommend our hyperheat units, which give you 100% capacity down to 5 degrees outdoors. And then you still get about 75–80% capacity at -13. So heat pumps do work in cold climates. Some of the design benefits, that's actually a shot at the inside of the tiny office there. So having multiple indoor unit types gives you a lot of design flexibility. Again, ductless is what we really lead with, but we also make less duct units, like those horizontal ducted units, that require less space. So a lot of times we have attics and crawl spaces as a place to store our heating and cooling equipment. A lot of times people have started spray foaming the roof in order to keep their heating and cooling system inside conditioned space or inside the thermal envelope of a house. So we like to say, you know, we can show you how to keep everything inside conditioned space without bringing all that additional attic volume into the equation. Some of the application benefits, they're easy to install, and as you know, time is money, so if we can reduce the amount of labor time that installers have on site, then it should reduce your cost. Room by room comfort, longer lifespans of the equipment. These are extremely durable. We have less than a 0.05% failure rate. So I'm not saying it never happens, but it rarely happens. And, you know, not trying to throw anybody under the bus here, but we often find that it's an installer error. It's nothing related to the equipment itself. Just tell you a quick story. We had an issue with the equipment on the tiny office. It was not cooling. And, you know, suddenly fingers start getting pointed. People start getting blamed. But we brought one of our technicians out and they discovered it was just something that come loose in transit. So they put it back together and everything's working fine. So it's usually something simple. And again, extremely quiet, both the indoor and the outdoor. So this doesn't apply so much to tiny houses, but you know, most of us don't live in tiny houses. They're slightly larger than that, and they have multiple rooms. So we like to say that would it make sense if you turned on a faucet in the kitchen and all the faucets in the home were turned on? You wouldn't think of doing that, right? That would be wasteful. It would be insane. So no, we wouldn't do that. So we zone our plumbing, correct? Do we zone our lighting? If you come in and flip a light switch, do all the lights in the house come on? I wish I had a light switch where they would all turn off. That would be great. But no, we don't. We zone our lighting, right? So what we're advocating for is zone comfort solutions is what we like to call it. So having the ability to control your comfort in any part of that home. And if you're not using any part of that home at a certain time, you could literally just shut that system off. So it gives you a lot of flexibility, and it also gives you a lot of individualized, sort of customized comfort in each space. You get to decide what temperature you like it in the room that you're in, as opposed to everybody fighting over what the number should be on that little box on the wall in the hallway. Does that happen at your house? Never. That's what I like to hear. That's because you're a mechanical engineer. So the three tenets that we're really trying to promote under our zone comfort solutions are comfort, efficiency, and health. I believe those are three of the four tenets you mentioned on your last slide. So you hear this a lot in the high-performance homes industry, but we're obviously going to focus on comfort because that's why you buy a heating and cooling system in the first place. And in addition to individual room comfort, we also talk about that quiet operation as part of the human comfort equation. Efficiency, our inverter compressors that vary refrigerant flow, the variable speed fans in our air handlers, all that leads to much more efficient equipment as well as lower energy bills. And then human health. I mean, we want to make sure we have healthy homes to live in so that people are breathing healthy air. So most of us have a central return out in the hallway, and we have one filter to change, and we think that's really convenient, assuming you remember to do it. But what we're doing is we're filtering air at each of our air handler locations. So you have what we say multiple points of filtration. And then again, we are advocating for eliminating ductwork if possible. Carl was able to do that in his house. And if you can't completely eliminate it, at least going with less duct. That's all I got. I think that's as long as I can talk anyway. Great, yeah, we got a little extra time. So, somebody had a question over here. Carl?
What was the little black box that you touched on? Something about the little black box.
Magic box, ERP.
For ventilation.
Yeah.
Yeah, it's called energy recovery ventilator. It brings in outside air, it's got a core, and then it basically filters the air and transfers either heat or cool and or humidity in or out, depending on which season it is. So basically, it's not like super efficient, but it's better than just bringing outside air in. It gives you some temperature in the air, so the air coming in is really cold or really hot. So there's for small houses, there's Panasonic makes a couple that are very good. They're small, really easy to operate. Yes.
So in a tiny home, there's several challenges. One, the 8.5 feet width. Now when you're trying to put insulation, etc., your materials, you've got different framing options like 2x4s, some metal framings, that kind of stuff. You want to try and minimize the thickness of the walls and yet still maintain insulation. What options give you, say, the least thickness walls, and what can you do?
In our climate, the wall insulation is not your highest priority, so our 13 is manageable, our 19 is better. You could go with a rigid foam that would get you that R7 per inch that you can get really good R value. You go with closed cell spray foam, which is about the same, so you can get R21 in a 3-inch wall. Or if you just, I think in general, you'll do okay, just get R13. Pretty much any insulation, as long as it's a small ride with an air barrier, will get you what maybe colder climates and exterior continuous insulation is a good idea. And probably a little bit more in your roof, at least R19 in the roof if it's foam insulation.
Did you mention metal stuff?
Yeah, one guy there.
So if you're going metal for your structure, then I would go to rigid foam route.
Yeah.
Wrap it on the outside.
Yeah, but do continuous insulation and then probably cavity
Well, like
insulation.
a commercial
Yeah.
construction.
Go to, yes.
I know that
Passive house, you're actually confusing passive solar and a passive house. They're actually not the same. Solar design is oriented the house so that you don't get heat if you don't want it. You take advantage of the heat when you want it. You could theoretically do a tiny house on wheels that is designed for orientation and just make sure to always point it in the right direction. You know, you would have to basically minimize your east and west windows, and you could maximize your north windows in our climate, and then your south windows, you want to have a medium amount of south windows with proper shape. And as long as you face the south side of the window south every time you park it, you would get that opportunity. One of the problems with trying to go passive solar is that in a particular climate like this, you would get a lot of heat in the wintertime when it's actually pretty warm out. Passive solar tends to work better in a colder climate where it's continuous cold in the wintertime, where the light coming, the sun coming in actually does heat the house. Here it's going to tend to overheat the house a good portion of the year.
Yeah, mild winter days, you have to your air.
Yes. Yes. Yes.
Could you put back the slide that had green
Greencurmudgeon.com.
There were some other contact information.
I'll let him do that while we're at it. I have cards too. Yeah.
When it comes to putting internet inside of a tiny home, I see that you have all these like planning out from the get-go how you want the house to be working on. So how would like running a fiber optic or running a cable line in there work, or is that even possible?
I'm not sure. If it's a house on a foundation, then you just do it like a regular house, bring a cable or bring whatever service you want in. If it's mobile, I would think you probably just use wireless internet. I can't imagine any way to plug it in. Yes. Yeah, fireplaces are bad. You should never put a, if you want to have a house, do not put a fireplace in. Put a fireplace outside. No, the only kind of fireplace you really should have in a house is a permanent sealed glass front fireplace that has direct vent. Fireplaces are a mess. Well, I mean, these are cramped built houses and a little wood stove. It's like, okay, in a regular house, if you want a wood stove, you want to use a sealed combustion wood stove. Any kind of fireplace that's open, all it does is pollute your house and suck heat out. The only two things it does. Yeah, right, but if it's a permanent glass front that's got a direct vent outside, those will actually heat the house and keep the noxious fumes out of the house. Any kind of open fireplace is useless for heating or air quality.
There's another problem with a fireplace, which is you got a air barrier to start with.
Right, an open fireplace in a tight house is just, it's a disaster waiting to happen.
If you can get it to light, you won't be able to get it to draft, so it's a bad idea.
Yeah, no, it's just a little heater, yeah. It's some kind of little wood stove. I'm not sure what it is. I would not ever do that unless it's totally sealed and directly vented out of the house. I would never do that. I mean, that house will probably keep the windows open most of the time. Then it doesn't really matter. Yes, sir.
Hooking up a echo beam to the Mitsubishi system with multiple rooms, is that possible?
Yes, so his question was, can you hook up an Ecobee or a Nest or any of the learning thermostats to one of these? Yes, we have what's called a thermostat interface, so you can bring any third-party stat that's too heat, too cool. If you have more questions about that, we can talk after. Yes, it's absolutely possible. Carl actually used a Honeywell Lyric in his house with our equipment, so you just bought the interface.
I understand that a spray foam insulation is a bit toxic. Does that toxic level change after it cures? And are there benefits to going with insulation more traditional?
Spray foam does have some toxicity to it. Generally, if it's installed correctly, which means that the installer did it at the right temperature, the right mix, after a few days, it's basically going to be fine. I chose to not use any foam insulation in the house I just built. It all with blown-in fiberglass insulation, just to try something different. And a lot of it's a matter of design. I think that if you're building a new house, There's no reason you would need to use foam insulation unless you made it such a complex shape that regular insulation doesn't work. So, you know, there's nothing inherently bad with foam insulation, but the challenge is it's basically, you're building a factory and a truck, and they're manufacturing a product on site, which is inherent, creates inherent problems. So generally it's not a problem. There have been stories of people having continuous off-gassing, but if it's done right, it tends to not off-gas after a few days.
The breathable house you originally said was a no-no.
But houses shouldn't breathe.
That was why I was taught houses should breathe.
Well, houses should be ventilated, but the only air coming in and out of a house should be controlled through ducts if you know how it runs. You should never breathe randomly because it will only bring in the stuff you don't want. What else?
Maybe the price difference, that's why between the treatment that you are presenting
In a standard heat pump? Yeah, I mean, so pricing is something I hate when people ask that question. Because I'm the manufacturer, so I don't actually sell to the end user, so I can't really quote pricing. But, yeah, I mean, that's right, from Carl's, what he just said, if you can hear that, is it depends. I mean, so if you're comparing it to a standard 14-SEER heat pump, then sure, it's going to be more expensive because it's better. You would basically, the only way you could do a fair comparison would be a conventional unit, their highest SEER, equipment that they offer, which for most, unitary manufacturers, that's going to be somewhere around 18 to 20 SEER, and we're somewhere between 25 and 33. So it's really just not a fair comparison. So yeah, it's going to be a little more expensive to get this type of technology, but
Probably going to be comparable price to a very high performance, really well designed standards.
What's the standard life expectancy from the manufacturer? What's the life expectancy of each unit?
yeah, I mean, I think properly maintained, you could be talking 20 to 30-year life cycle. We have if it's installed by one of our certified diamond contractors, as they're called, it's a 12-year warranty, which is the strongest in the industry. But yeah, we certainly expect it to last a lot longer.
You said you have the smallest and half time, but I noticed a lot of teardrops, high-end ones that take longer. Do y'all have any actual doing smaller teardrops?
Yeah, great question. So we are in the process of developing a smaller system right now. Yeah, we expect that to be available in the next year to 2 years. Yeah. So there's a lot of demand for that, as you can imagine, with houses of this size.
And that applies to
That's right. Yeah, I mean, it could be a lot smaller than this even. Did I see another hand go up?
Thank you.
Thanks, guys.